Hello and welcome to another episode from High Output AI. I'm Tom White. I got my dear friend Elliot Smith here.
What is up? We are in person. That's a nice change.
We've done it. We look like we're having a therapy session together, but we're not. We're actually here to talk about U-Net today, which we're very excited to do. So, Elliot, you ready to talk about U-Net and all things U-Net after your live stream that you did the other day?
Absolutely. And everyone say hello to MIDAS as well. He's likely to come in and out of the clips every now and then.
Fantastic. So today we're going to be talking about U-Net and the original 2015 paper that came out of the University of Freiburg. And we're going to be talking about how it was a step change in segmentation of images, especially in the biomedical world. And we know there's been a lot of development since 2015, but today we're going to go back to the fundamentals and back to the main theory behind when this paper was released. So to start off, I know you know a lot about it ever since your live stream, and if you haven't checked out Elliot's live stream yet, we'll put it up here somewhere. Yeah, one of these things up here. And obviously, if you haven't subscribed, you haven't hit that bell button, please do. Please join our ever-growing subscriber list, and press the buttons down here. Do the thing. You guys know what to do. But yeah, we'll jump into it. And what I think we'll do is we'll jump in a little bit of a background on the model, if you've got some historical context for us, and kind of a high-level overview of what the model does and why it was developed and what the real innovation was from it.
Sounds good. And I will be doing more streams on U-Nets and some of their more, say, modern derivatives, adding things like ResNets and attention in. So do check those out. Best way to get notified is when they're streamed, but they will be normal videos after the stream is done. But if you want to come in and ask questions, that's the best way to get that done.
Yeah, we'll be releasing that stuff on Twitter, and all our Twitter details will be in the show notes below. So
Indeed.
Take us away, mate.
Yeah, so the U-Net model, it's pretty popular. You'll find it everywhere. It's in Stable Diffusion. A lot of these image-to-image based models, it's kind of the go-to standard for segmentation these days, and for good reason. So, as you said, 2015, it came out of some of the challenges of segmenting biomedical images. In its original use case, it was microscopy. A lot of sort of cells, biological data, pressed close together that needed to be segmented into individual cells for things like cell counting and later classification of that tissue.
Would you say those challenges came about because the medical world has a need for accuracy and also a very different data set compared to the normal image segmentation world?
Yeah, definitely. I mean, look, in the medical world, which is where Tom and I have spent a lot of our time doing AI and working on AI projects, there's a huge amount of image data, and a huge amount of it needs segmentation. So you can imagine segmentation to be sort of anatomical level segmentation. So find different organs in a X-ray or a CT scan of the body, or I guess more nuanced classification, which is healthy tissue versus, say, cancerous tissue or damaged tissue, for example, all the way down to, I guess, the smallest part of the human body, individual cells. So classifying those cells as healthy or classifying what type of cells they might be, that's all achievable through segmentation models. And U-Net is, and for the last 7 or so years at least, the new de facto way to get that done efficiently.
Fantastic. And talk us through some of the changes that they made from the previous work, how they went about it, and what the core innovations of the product were.
Yeah, 100%. So, look, the image-to-image world was not brand new when U-Net came out. Things like autoencoders, multi-layer convolutional networks, they were all around at that time. The big innovation within the U-Net space was the skip connections that you see between the downward layers and the upward layers. And that really enabled these models to do a much, much better job at segmenting. And really filled that niche. This model was used in a number of competitions that were running at the time around segmenting various biological structures, both in microscopy and in, I think, MRI. And it performed really well and really has since taken the segmentation world by storm and is now just about everywhere.
So there was a major innovation in the architecture, which you talked about a little bit there, but there was also a bit of an innovation in how they trained it, right, as well, and using augmentation, which was a bit different to image models being trained in the past.
Yeah. So, biological data and biological images tend to be a little different from your everyday picture. If you're snapping pictures of your dog, of which I do, there's a lot of pictures of my dog on my phone, it's pretty normal that you'll get changes in lighting, changes in contrast. The dog will be closer, the dog will be further away, sort of normal camera-like changes. I can open this blind and close this blind and change the lighting in the room quite significantly. And for a long time, the way that we did image augmentation for image models was to say, let's randomly adjust the brightness and the contrast or the color temperature, because all of those are valid ways that we can adjust that image and still have 1, 2 human beings and a dog that could then be segmented. In the biological imaging space, a lot of the equipment that captures the images is very highly tuned, very highly standardized. So the types of changes you see tend to not be the same as you'd see with a camera or with the smartphone. So this work looked at changes, especially around elastic deformation, which is very relevant in the medical imaging space. And to go in a little bit about what that is, there's a couple of different types of ways you can distort an image, and that's called deformation. Now, inelastic deformation, often called affine transforms, and I guess it's the basic stuff you'd think of when you talk about image augmentation these days, is things like zooming in. It's things like rotating the image, even skewing the image. And what it does is you imagine the whole image itself as a rectangle that you're stretching, rotating, squeezing, whatever you do. But in the biological imaging space, we tend to also look at what's called elastic transformation or elastic deformation. And that's saying that different parts of the image may need to or can validly be adjusted differently. So for example, if you take a look at my face here, my cheeks can be shaped and prodded and moved around and really changed in size in quite a dramatic way, while still being valid as cheeks. Other things, like my bones, they can be squished and deformed, but that's not really a good outcome for my bones, at least. So what elastic deformation does, in the very naive sense, is it will change different parts of the image differently. So you could imagine elastically deforming this view of my face by increasing the size of my eyes, moving my mouth to the left, moving my chin down, all of that sort of stuff. And while on a face, that's a little bit of an odd thing to do, if you're thinking about images of an individual cell or a collection of cells, or perhaps the internal organs within the body, let's say the lungs, which naturally inflate and deflate relative to other areas of the body, we can do those deformations in a way that's still, I suppose, biologically valid, but not necessarily captured in the real world, but we make those transformations. And that gives us more data to use in our training of the model. And in this case, it seemed to really help. And the original U-Net paper and its subsequent versions have had really good performance as a result of some of those additional tricks, which are not just changes to the model.
So those non-linear transformations really helped provide more data to the model in a world which might not have that much data or might be very difficult to obtain that data. That was a clear benefit of this training methodology and this model implementation. Now, what other benefits come to mind for you of moving to a U-Net world away from the previous world?
Extract features. Yeah, so the U-Net on the downward side of the U data efficient in that with a smaller number than traditionally seen examples, it can get pretty good segmentation results. So some of the data I've been working on in the streams all the way down to 3,000 images small but very feature-rich representation. And it can get quite high accuracy. And then it starts to come back up images. So it takes those smaller much more images than sort of its earlier predecessors. 1024 which is really good. Bottom, as Tom alluded to, in the medical world, it'll gather in new imaging data and start to run convolutions, and there's only so many times you can take a X-ray of somebody's chest before this. Now, if you've ever built a autoencoder or similar models, you may say, okay, this is pretty similar to what we've had in the past. And it absolutely is. Where the U-Net differs is that as it goes back up the network, the feature maps from the different downward steps are concatenated to the new features and then used to take that next upward step. And what that means is that you get features from much earlier in the model coming in and contributing to the features very late in the model. And this is, I think, the big innovation in the U-Net is these concatenations, and it really does seem to be a big contributor to why this model performs so well. And you can see this idea of sort of combining earlier features and skipping earlier features has become a lot more prevalent even in other model designs like, say, ResNet, where that's done at a much smaller scale, but features are, in that case, added together to start to make use of them later in the model.
So that's a good point to start moving forward a little bit, I think. So U-Net stormed onto the scene in 2015 and took the world by storm by winning all those competitions and changing how we do segmentation. Now, can you talk us through what's happened in the preceding in the 7 years? We're filming this at the end of 2022. What's happened since then, and where are we at today?
Yeah, so look, the U-Net at its core, the fundamental go down, go up, make skip connections, that is still everywhere. It's in stable diffusion, it's in a lot of image to image, a lot of segmentation. What we've seen change is that the way that those intermediate steps are processed, what was originally a convolution, and a max pool, we've seen a lot of innovation in that space. So we've got ResNet blocks, we've got attention blocks, we've got something much closer to, say, modern transformer architectures at different stages throughout that network. And that's allowed us to achieve much more complex tasks than segmentation. So it might be image to image, super resolution, things like that, in a very diverse and broad use case. If you look at stable diffusion as an example, it's quite popular at the moment. It has the capability to generate images in a number of different styles of a number of different things, and that's really only possible because there's more complex architecture under the hood. If you tried to build a stable diffusion with the U-Net architecture and the number of features from the original paper, your model likely wouldn't have capacity to perform a lot more of these complex actions.
So we've seen this model get applied to the new world of image generation, especially with stable diffusion. Have we seen any other commercial applications of this model for U-Net yet? Anything else new?
So it's hard to know exactly what's in a lot of these commercial models, but if you look at a lot of the industry papers around sort of segmentation in the medical space, classification of, say, tumors and things like that, a lot of those will have U-Net in there if they're doing pixel level segmentation. There is obviously the whole world of object detection, which is the topic for another video. But if you're really doing a lot of semantic segmentation of whatever it may be, especially in our field, the medical field, U-Nets do seem to be a pretty popular contender for a lot of papers and a lot of conference posters.
And do you think someone like Tesla, as you mentioned in object detection, is implementing something similar? Obviously hard to tell because it's very proprietary with Tesla, but...
Yeah, look, I don't know. I think certainly somewhere in the life cycle of the sort of vision autopilot that they've got, there's probably a U-Net-like structure in there. I'd be very surprised if it didn't have one. It may have moved on to something else as the team there tweaked and really made it a lot more driving specific. But yeah, I believe that in most cases, the savvy AI engineer these days will start with the U-Net if their task is segmentation or, I guess, image to image in a lot of cases.
So we've been singing the praises of U-Net for the last 20 minutes or so now. What drawbacks are associated with it? What trade-offs do you need to make when you're deciding to use a U-Net or not use a U-Net in your model?
Yeah. So I think the big one that I see a lot of people run into is, I guess, a more fundamental question about whether they truly need segmentation at a pixel by pixel level. The reason that is kind of a drawback is that you do need pixel level labels to make that work. Somebody has to go in and really finely outline whatever it is you're trying to segment, which can be a lot of work. And a lot of the problems I've seen, in the medical world and just generally within industry, probably would get by fine with, say, bounding boxes. So, we want to know that there's a person, or we might want to count the number of sheep in this image, but you don't really need to know pixel by pixel whether part of the image is a sheep or whether it's part of the background. And bounding box labeling can be much faster. Things like the different YOLO networks are designed to be very, very quick and are often, in a lot of these cases, a more appropriate model to use.
So that's an interesting point on how the limitations actually you're seeing aren't actually with the model itself, but the application of the model incorrectly. Maybe changing the question around a little bit to what bottlenecks or constraints do you currently see with U-Net that is either getting worked through at the moment or will be worked through in the future, or you'd like to work through even, for anyone listening out there?
Yeah, definitely. So one is you need a lot of data. The other one is that because we're fully convolutional, we're getting a large amount of feature maps. Modern GPUs, even if you have a big cluster of GPUs, they're going to run out of RAM very, very quickly, which means that a lot of these U-Net models, the data passing through them tends to be a scaled down version of images. Otherwise, you make the trade-off of a very small batch size and then much longer training times. And that can make some things difficult. They're often limited to 2D because 3D data, again, just ups the RAM usage a lot. You can imagine a CT scan of the human body at a sort of 1 millimeter cubed resolution. That's going to be hundreds of layers of, let's say, 512 by 512 or maybe up images. And you're very quickly going to fill the VRAM on your GPU or your cluster of GPUs if you're trying to do a large batch there and get those 1,024 features, even once you've done a number of different downscaling steps.
So these models very quickly become only available to people with large amounts of compute, i.e. organizations or institutions. So we're not going to be seeing as much playing around with it as we would, say, within the image generation world.
Yeah, I mean, there are things you can do. You can downscale your images. There are tweaks you can make. And really, it's a training time constraint. You can run Stable Diffusion on a MacBook, on the M1 chips, for example, which is not a huge sort of complex GPU architecture. And it runs pretty well. But, we are limited a bit by that. There are people doing things like patch-wise U-Nets, which will take an image and break it into overlapping patches, which is actually in the original paper. But, that does have its limitations as well in that the more detailed your original image is, the less sort of spatial zooming we can do by adding more down layers, which gives us some limitations on what type of features we can pick up in the final segmentation. But it's a bottleneck rather than a hard wall in that there are ways to get around them if you need to.
And sadly, the answer is, as always, more GPUs.
Yes, buy more GPUs.
So if you were sitting there in the office today and your boss came along to you and said, Elliot, we need to segment this image, go. What questions would you be asking yourself to whether you should use a U-Net or whether you should be considering other options? And what other options would you consider?
Yeah, I think number one would be, as always, what data do we have available and who created the labels? If we have a whole bunch of data, maybe there's publicly available data sets. Let's say I suddenly work for a self-driving car company. We've got a lot of road data. We can start to make use of it straight away. I'd be pretty happy with the U-Net. If we're segmenting, images from the latest deep space telescope that nobody has bothered to label yet, and there's not a lot of good training data, and these images are massive, I would say, wait, hold up, let's reconsider this, because there's going to be a gargantuan labeling effort here. And do we need pixel by pixel level answers, or should we be getting somebody to draw, say, bounding boxes, which, if you click and drag a bounding box, that's much faster than painting in each individual area within a certain instance. So that would be my starting point. Then I suppose I'd want to know what the application was. We've seen these segmentation setups be used to, say, estimate volumes of things. Let's say in the medical imaging space, we get the size of a brain. We know roughly how big a volume one pixel contributes to, and we can estimate the volume of somebody's brain. In those sort of questions, it's, what are we actually trying to get out here? Do we need that volume for a particular purpose? And what's an acceptable amount of error? Because while these models are quite good at segmentation, they're never going to be perfect. If we need it within, 30 to 40%, I'll say, yep, sure, this will work. But if we need it down to the cubic millimeter, we're really going to have to start to ask questions about why we need it so specifically, is there a better way to measure it, and so on.
Fantastic. Now, I'll put you on the other side of the table. You're now the boss, and you need to approach you've got engineers approaching you wanting to implement a U-Net, and you're concerned about all these things that you've brought up. What questions would you be what questions would you be asking your engineers, or information you'd be gathering from them to make sure that they are spending the appropriate time on implementing a U-Net or not?
Yeah. I'd first look at what metrics they were judging their performance against. That might be the DICE coefficient, which is a measure of how well does our predicted label match with a ground truth label. And then making sure that they have reasonable benchmarks. So how good does this have to be? How good does the naive approach work? Let's say, putting a box around it and assuming that everything is roughly a circle. So what's the volume of a circle within a box of a certain size? How does your model, which is adding extra layers of complexity and compute time, differ from that reasonable benchmark? And if the incremental gains that we get from this model start to fade away, drop off, we need to say, let's stop spending our engineering time on model development and start focusing that effort somewhere else where we can get more business value at the end of the day. Because in the real world context, from a research academic perspective, you can tweak these models to your heart's content. But in the real world, when we're using these models for solving real problems, we always need to be aware that we're making trade-offs in training an extra model, adding extra features to the model, and we need to balance those trade-offs.
We made a video a little while ago detailing the questions you should make sure you ask before you start any work on AI. We'll link that up here somewhere. Another question then is you mentioned bounding boxes as a more simplified version of this instead of the detailed U-Net pixel by pixel. Are there any other alternatives you would consider before you went ahead with a U-Net? Because obviously a U-Net has a much higher burden on the labeling required.
Yeah, it would depend on the nature of the problem. I've seen some people do pretty well with models that, let's say we were talking about that brain volume prediction algorithm. I've seen some pretty good models where we take the image, we have a number of convolution layers and then a couple of dense layers, and we actually predict the volume of the brain directly, as an example, and that can work depending on the context. And to give you an example there, we might independently have data on brain volume or heart volume or lung volume or things like that that's much more easily available than a pixel by pixel segmentation of the brain. And if you have a big enough data set, you can get a very good model from that reduced data set, that, I guess, lower complexity data set, compared to going through the effort of doing that pixel by pixel segmentation. We had similar stuff with prostate volume in some of the work we did back in the day, where radiologists would estimate the volume of the prostate by taking a width, a height, and a depth, and assuming it's roughly spherical. And that worked pretty well to test models and to calibrate models alongside a small amount of data that had been labeled pixel by pixel.
So have you seen any hybrid approaches using a U-Net and like trying to make a better trade-off between the high requirement of labeling versus the accuracy of the U-Net at the pixel by pixel level?
Yeah, so you can do a lot of unsupervised training in U-Nets as well, which allows you to take sort of raw, unlabeled data and start to pre-train your network to then be refined into, say, a segmentation task. So we might do, say, denoising, where we'll take images, we'll add noise to them, and we'll try and either predict the noise or predict the noise-free version of the image. You might do in-painting, where you blank out a section of the image and you try and get the U-Net to predict what was there. Lots of different things you can do, which means that, let's say you have a small number of labeled cases of, let's say, cats and dogs. You can then just scour Google for any images of cats and dogs, do some of these unsupervised techniques, and then once you've got that pre-trained network, refine that on the task of segmentation.
Can you tell me about ResNet?
So yeah, I mean, there are lots of different variants of U-Net these days. One of them typically that you'll see and appears in Stable Diffusion is to replace those convolution blocks with ResNet blocks, which have multiple convolutions. They have residuals, hence the res, and that gives us a bit more complexity, a bit more capacity at each of those different stages to predict and produce, I suppose, more refined features that can then be used for more complex tasks.
Well, mate, thank you very much for that detailed explanation. MIDAS thanks you, and I'm sure our dear followers and listeners and watchers are thanking you as well. Any final comments or thoughts on U-Net or just general excitement? Because I know you're pretty pumped about this space at the moment.
Yeah, look, there's still a lot going on. I would recommend anyone trying to get into this, build a couple of simple models, learn how they've improved over the years. Obviously, if you're in a very applied space, try and get an off-the-shelf model because you're not here to innovate on models, you're here to apply them. But there's so much going on here. It might seem like everything's been done, but honestly, even since we started, which was about 6 years ago, just after the original U-Net paper came out, there's been such a change in how these models are put together. And it's a very exciting time to be in the image space within AI and I think AI in general. So keep up the good work, everyone, and excited to see what you all build next.
Well, thank you very much, everyone. Make sure you subscribe to keep getting videos like this and to see the live streams that Elliot does. Leave any comments, any questions you have in the comments. Give us any feedback. Say hello to MIDAS. Do whatever you need to do in the comments. But thank you so much for watching, and we'll see you next time.
Bye-bye.